Hello everyone! In this ROS2 Jazzy tutorial, we explain how to write a C++ program and a ROS2 package from scratch that demonstrate how to implement all the components of a controller for controlling the position of a mobile robot in 2D space. The goal of the controller is to steer or to move the robot from the initial position and orientation illustrated over here to the desired position represented by this point D over here. The control algorithm has this form, that is, it consists of these three equations that will be thoroughly explained and derived in this video tutorial. As a test case and to visualize the motion of a 2D robot, we are going to use a TurtleSim simulation environment shown over here. Namely, a robot is represented by this turtle over here that can move in this two-dimensional world. As a test case, and to illustrate the performance of the controller, we are going to use a TurtleSim simulation environment. A TurtleSim simulation environment is a very useful ROS2 simulation environment that enables us to test the behavior of controllers in a two-dimensional world. Namely, a robot is represented by this turtle over here that can move in this two-dimensional world. That is, it can move forward, it can rotate, and by using these two operations, we can actually describe any trajectory or control the robot position. Over here, for illustration, we are going to set the desired position to be on the x-axis 1 and on the y-axis 9. That is, 0, 0 is over here, and on the x we want to go here, and on the y-axis here. Consequently, we need to go to this point. So let's illustrate the controller behavior. Over here, I'm going to run the controller, and you can see the behavior of the position controller. Here it is. You can see how the turtle describes the trajectory, and it will slowly approach to the desired point 1, 9. Here it is. Here we deliberately slow down the controller in order to illustrate the animation. Now let's see what happens after we increase the controller speed, and here it is. You can see how the controller reacts relatively quickly. And here we are. Literally in less than basically 2-3 seconds we arrived at the desired position over here. In this video tutorial, we explain how to implement from scratch a ROS2 package and ROS2 node that implements the controller, as well as the C++ code shown over here that controls the robot. In addition to this C++ code and the ROS2 package, we created a manual that thoroughly explains all the steps that you need to perform in order to implement the controller and to write the ROS2 package. Here is the manual. This manual contains, I think, around 12 or 13 pages. In addition to this, we created a separate document shown over here that explains the basics of the position controller for the mobile robot. Here's the document. It contains thorough derivations of the controller and all the equations. The code, these two manuals, as well as additional files, will be given in the description below. That is, links will be posted to these files. Here are the license and the copyright notice. This document, develop code files, lesson video, and all the provided material referred to as learning material in the sequel should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Also, the learning material should not be reproduced manually or automatically using, for example, an algorithm or an AI model from this video and then posted on public or private online repositories. The provided code files and learning material are the ownership and the original work of Dr. Alexander Haber, who is the author, and they are for personal and non-commercial use. You have the right to use the provided code files and learning material for personal educational use and strictly for non-commercial use. The code files should not be used for commercial purposes without paying an appropriate fee to the author. The code files and the learning material should not be used as lecture material on online learning platforms and in official or unofficial university courses. Without the permission of the author and without paying an appropriate fee, the provided code files and learning material should not be used to produce academic papers, student reports, or other documents. The provided code files and learning material should not be used to train an AI algorithm or a large language model. Okay, let's start with explanation. First of all, let's talk about prerequisites. To implement the material presented in this tutorial, you need to have number 1. Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. You have a number of video tutorials on my YouTube channel explaining how to do that. Next, let's verify that you have the proper Linux Ubuntu version. To do that, first open a terminal by clicking here, search for terminal, and over here I'm going to resize this terminal window such that you can see what I'm typing, and at the same time you can follow the manual and all the commands will be written in this manual. Okay, to verify the Linux Ubuntu distribution, you need to type this. And you should see Ubuntu 24.04. This last number really doesn't matter. These two numbers are the most important ones. Next, you need to have the proper ROS2 version. This video tutorial is developed under the assumption that ROS2 Jazzy Jalisco is installed on your system. My suggestion is to migrate or to switch from older versions of ROS2 to the newest version Jazzy Jalisco. This is mainly because the final end-of-life date or the end of support for ROS2 Jazzy Jalisco is in 2029. This is 4 or 5 years from today. To verify that ROS2 Jazzy Jalisco is installed, you need to open again a terminal or use the same terminal, and then you need to simply type this command. This command will list the content of this folder, and over here you should see something. If you see something, this means that Jazzy folder is non-empty, and this means that most likely ROS2 Jazzy Jalisco is installed on your system. However, the proper verification is to try to execute the setup.bash file from the ROS2 installation, and we do it like this. If you can execute this command with no errors, this means the ROS2 Jazzy Jalisco is installed. Then you can print the ROS2 version by simply typing this. And over here you should see Jazzy. If you see Jazzy, this means that ROS2 Jazzy Jalisco is properly installed on your system and you can continue. If you don't have ROS2 Jazzy Jalisco installed on your system, then go to my YouTube channel and you can find a number of tutorials explaining how to install ROS2 Jazzy Jalisco. The first step is to install and start the TurtleSim node and simulation. However, before we do that, we need to create an underlay. So let's start from scratch and let me explain you what is an underlay. I'm going to spend more time explaining the basics of ROS2 since I believe that a lot of viewers of this video are completely new to ROS2 and to the whole concept of creating an underlay and overlay. The underlay is a basic ROS2 configuration and a set of parameters created and defined by sourcing a setup script provided by the standard ROS2 installation. The underlay provides the necessary build dependencies, libraries, and packages necessary to execute the ROS2 commands and build packages using the Colcon build system. Colcon build system is a very similar build and compilation system to CMake. The underlay is created by executing the following command in the terminal. That is, we need to execute this. This command we actually executed previously. And this command will run the setup.bash file. The setup.bash file will create an underlay, that is, it will set all the ROS2 parameters such that we can use the callcon build system. So simply run this and you have created an underlay. Now, after we create our package, and this will be explained in the sequel, we need to create an overlay. The overlay is a configuration in a set of parameters that enables us to execute programs and nodes of the created package. So the story goes like this. First, when you want to develop a new package, you create an underlay, then you will build that package, and then after that, after you create the package and you want to use the created nodes, then you need to do an overlay. This will be explained in the sequel. After we have created an underlay, we need to install the TurtleSim package. Most likely the TurtleSim package already comes with your ROS2 installation. However, it's still a good idea and practice to try to install it. To install it in the terminal, first update and upgrade everything, that is, run this command. And remember, whenever you want to play with Linux Ubuntu or you want to play with ROS, run these two commands to make sure that your system is completely up to date. That is, that all the packages are up to date, and over here press Y and wait. To install the TurtleSim, you need to run this command. And then let's verify that TurtleSim is installed by typing this, and you can see all the packages over here. Good. Let's now run the TurtleSim simulation. To do that, we need to execute this command. And let's explain what we are doing over here. ROS2 run is the command for running a ROS2 package or ROS2 node. The name of the package is TurtleSim, and the name of the executable is TurtleSim_node. And if you type this, you will see over here this 2D world with a turtle over here. Unfortunately, turtle is relatively small, and I'm now going to close this window and I'm going to run it again, and you will see that the turtle animation is changed over here. And every time you close this window and you start it again, that is, you start node again, you will get a different animation. This cute 2D turtle is a 2D model of a mobile robot. We can control the position of this robot by sending the linear velocity and angular velocity commands. These commands are sent through an appropriate topic. We need to find out that topic name. To find the topic name, we need to open a new terminal, create an underlay, that is, source the environment, and type this command, ROS2 topic list. So let's do that. In the new terminal, type this, and then type this command. While executing this command, it's very important that the original window in which you're running the TurtleSim node is open. And if you click over here, the TurtleSim simulations should be active. If you go to this terminal, you should see all the topics. For us, the most important topic is currently Turtle1 command velocity. This is the topic that's used to send control commands. That is, the control method that will be implemented in a separate node will use this topic to communicate control commands that will move the turtle. On the other hand, our node, which is actually TurtleSim, receives these commands and it will move the turtle. The next step is to figure out the type of ROS2 messages that are sent through this topic. To do that, we need to type this command. Before we execute this command, let's explain what's happening over here. ROS2 topic info is the command that's used to get more information about the type of messages being sent through an appropriate topic. And over here, we want to investigate this topic, and let's see what's happening. The type of message is geometry message twist. So it's a twist message. Twist message is a separate and defined That is, this is basically a message that's being defined inside of the ROS environment, and it's a basic data structure. Then we can see over here how many publishers we have that are publishing to this topic, 0 publishers, and how many subscribers we have, only 1 subscriber. And who is the subscriber? Well, the subscriber is actually our TurtleSim node. That is, we have already subscribed ourselves. That is, this is done automatically to this topic. However, we don't have the publisher and we need to create our publisher. This is very, very important. Let's obtain more information about geometry message twist. To do that, we need to execute this command. This command will actually show what are the member variables of this data structure twist. So let's see what's happening. Very interesting. We have 2 components and every component has 3 entries. Consequently, geometry message twist contains 6 entries, and they are components of the linear velocity and components of the angular velocity. Here, it's very important to keep in mind the following. Since we live in the 2-dimensional space, certain components will be automatically set to 0. Namely, in the case of the angular velocity, we are not going to have angular velocity around x and y axis. Consequently, these 2 components will be equal to 0. We are going to only have the component around the z-axis. However, to better understand this, let's explain how the coordinate systems are oriented. The origin of the coordinate system is located over here. And then we have the x-axis and we have y-axis. However, this is actually the base coordinate system. In this particular case, we are actually communicating messages inside of the body coordinate system. I'm going to explain body and base coordinate systems later on. For the time being, it's very important to understand that the body coordinate system is the coordinate system rigidly attached to our robot. That is, it is at the center of this turtle and it can move with the turtle. However, it's still rigidly attached. Consequently, these velocities over here are actually defined in that body coordinate system and not in the base coordinate system. This will be explained later on in this video tutorial. Next, let's run again ROS topic list and let's see what will be the output. And this time let's focus on this topic over here and let's explain what it is. First of all, let's obtain more information about that topic by running this, and we can see again. So the type of messages that are being sent through this topic are TurtleSim message pose. We have 1 publisher, which is our TurtleSim node, and we don't have a subscriber, and we are going to write a subscriber later on inside of our C++ code. So let's explain the purpose of this topic. This topic is actually used to communicate the sensor information. Namely, this turtle over here has a sensor. This sensor can measure several things, and the sensor information is embedded inside of an appropriate data structure of the type TurtleSim message pose, and it's being communicated through this topic. So let's see what is inside of that data structure. To do that, we'll simply need to type this command. And over here, you can see a very useful information. This data structure contains x and y coordinates of the center of the turtle inside of the base coordinate system. The base coordinate system is located over here, and consequently x and y will be the coordinates of the center of the turtle. In this case, they will be 5, 5, since the turtle is placed at the center of this mini 2D world. The third information is the sensor information about the orientation. The orientation of the turtle is simply the angle of rotation of the turtle. Currently, it's 0. And then we have 2 additional entries. They are linear velocity and angular velocity. Linear velocity is the velocity in the direction of the local x-axis, or in the body coordinate system x-axis, and angular velocity is the angular velocity around the z-axis of the body coordinate system. We are going to explain that in the sequel thoroughly. Consequently, our TurtleSim, that is our small cute turtle, is equipped with a sensor that can measure the position of the turtle with respect to this point over here, as well as the orientation, and it's going to measure the linear velocity and the angular velocity of the turtle. This information will be communicated to our feedback control algorithm, and that communication loop is actually a feedback that's being communicated through this topic called Turtle1 pose. Before we create our ROS2 package and implement our controller in C++, let's first explain the basics of the controller and let's derive the equations of the controller. For that purpose, consider this figure over here. This figure shows the 2D projection of the general 2D mobile robot. First, let's introduce coordinate systems. Coordinate systems are also known as coordinate frames or simply frames in the robotics literature. Let the center of the robot be denoted by the point B over here. At the same time, this point is the origin of the body coordinate system. The body coordinate system is a very important coordinate system firmly attached or rigidly attached to the robot body. To repeat, the body coordinate system denoted by B has the center at the point B. The axes of this body coordinate system are xb and yb. As mentioned previously, this coordinate system xb, yb is firmly attached to the robot and it moves as the robot moves. Besides the body coordinate system, we also have the base coordinate system, whose origin is denoted by the point O. Over here is the base coordinate system. Let's now go back to our TurtleSim simulation. So where is the body coordinate system? The body coordinate system is located over here at the center of the turtle body. Where is the base coordinate system? The base coordinate system is located over here. In our illustration, the base coordinate system is located over here. The base coordinate system is firmly attached to the ground and it doesn't move. That is, this is our world or inertial coordinate system that doesn't move. Next, let's introduce the orientation angle. The orientation of the body coordinate system, that is the orientation of xb, yb, with respect to the base coordinate system xy, is described by this angle theta or theta, however you would like to pronounce it. This is actually the angle that the axis xb creates with the axis x of the base coordinate system. Next, let's introduce the desired position. Let the desired position of the center of the robot body be denoted by the point D over here. This point is selected by the user and this is the final destination of the robot. That is, we want to steer the robot to this position. The coordinates of this point in the base coordinate system are xd and yd. Let's introduce the control objective. The control objective is to move the center of the robot body B to the point D. Here, we are not explicitly controlling the orientation angle theta of the robot. That is, we don't care what will be the orientation of the robot at the desired position D. We are just interested in steering the robot to this desired position. The control method presented in the sequel can easily be modified such that we also control the orientation at the desired position D. For example, we can first move the robot B point to the point D, and then we can simply rotate the robot around the point B or D in order to adjust the orientation. However, for simplicity of this video tutorial and for the brevity, we are not going to do that. You can easily modify our controller. Let us again focus on this figure over here. At any time instant t, the robot can only move along the direction of the body coordinate axis xb. This is because the robot has wheels. That is, this axis xb will always be tangent to the trajectory locally. This means that at any time instant t, the velocity vector of the point B, denoted by VB, is collinear with the axis of the body coordinate system xb. How can we change the direction of motion? Well, we can adjust the orientation theta. The velocity vector VB is actually called as the linear velocity, and that's precisely the velocity vector that you got over here when typing ROS2 interface show geometry message twist. Consequently, over here you will get the components of this velocity vector, and this is the linear velocity vector. And this is actually expressed in the body coordinate system, that is in the coordinate system xb, yb, and consequently over here x will have a non-zero values, y will have a zero value, and z will have a zero value, where z is perpendicular to our screen. To repeat, we will only have x non-zero over here, y and z will be equal to 0. This is mainly due to the geometry of motion. And here comes a very important part. We assume that we can control the linear velocity VB. Also, we assume that we can control the angular velocity of the robot body. Since the orientation angle of the robot body is denoted by theta, the angular velocity of the robot body is denoted like this, theta with a dot, where the dot notation is used to denote the first derivative of some variable. Namely, if you took a differential equation class or if you took a control class, then you know that if you have, for example, a scalar variable or a vector variable with a single dot, this is the first derivative. If you see double dots, this is the second derivative. To summarize, we assume that both the linear velocity VB and the angular velocity theta dot of the robot can be controlled. So what is the angular velocity? Well, the angular velocity is the speed of rotation of the robot around the point B. And we assume that we can control VB and that speed of rotation. The position controller should compute these values, and then these values are sent to the local controller that should move the robot and produce these velocities. That is, in reality, there is a position controller, and in this video tutorial we are actually implementing the position controller. However, in addition to the position controller, you also have a local controller, and that local controller will accept VB and theta dot, and it will make sure that these velocities are produced in reality. This local controller, which most likely is some form of PID controller or some mixture of PID with something else, will actually move the robot according to VB and theta dot. VB and theta dot that are set by the user are actually the desired values of the velocities or the set points. Here, we will assume that the local controller is infinitely fast and that the dynamics of the system can respond with zero delay. That is, we neglect the local controller and the system dynamics. That is, we neglect the inertia of the system. Of course, this is an abstraction and simplification that is often not met in practice. However, since this is an intro tutorial mainly focused on the position controller or kinematics controller, for presentation clarity and brevity, we will stick to these assumptions. Now, let's analyze this geometry over here and let's derive the controller. Under the assumption that the position of the point B is known, and this position is known since our turtle and our 2D robot is equipped with a sensor that can measure the position x and y in the base coordinate system as well as the orientation, we know everything about the robot position and orientation. Then, by analyzing this triangle and by using basic trigonometry, we can obtain the tan or tangents of this vector theta d is actually equal to this side over this side. The length of this side is yd minus y, where yd is the y coordinate of the point D, over the length of this side, and this is xd minus x, where xd is the x coordinates of the point D. Now, we can actually solve this equation, and the solution is given by the equation over here, where this a tan 2 is the inverse tangent with the second argument, or this is actually the two argument arctangent function. So why do we use a tan 2? Well, by doing a tan 2, we actually ensure that if, for example, this point is over here, then the angle will be between 0 and pi, or better to say between pi over 2 and pi, and the basic inverse tangent function cannot return this angle. It can only return the angle between minus pi over 2 and pi over 2, and consequently we need something else that will take into account where our point is located. That is, we need to take the quadrant of the unit circle into account, and this a tan 2 function will return the proper or the correct angle that can be from 0 to pi or from 0 to minus pi, and always use a tan 2 in robotics applications. So what is now theta d? We will call theta d as the desired angle. So why this angle is called as the desired angle? The significance of the desired angle comes from the following facts. Namely, if the orientation of the robot theta, that is this angle over here, theta, is equal to the desired angle theta d, then the robot moves along the straight line connecting B and D. That is, the robot will approach the desired position D. And this is very, very important. Consequently, if we can compute theta d, we know that we need to change the orientation theta of our robot such that theta becomes theta d, and in this case, the velocity vector will lie on this line and we will slowly approach the point D. And this is the importance of the desired angle. That's why we are using this equation over here to compute the desired angle. Again, we can measure the position x and y, and since we know xd and yd, we can simply compute this ratio, do inverse tangent, and we can always compute the desired angle. Note over here that as the robot moves, the desired angle changes, of course, and we have to recompute the desired angle at every position in space. And here comes a very important point. Our controller has to ensure that the orientation angle theta of t approaches the desired orientation angle theta d. Consequently, the simplest controller for steering the orientation angle to the desired orientation angle is given by this equation. Over here, theta c dot is the control signal in the form of the angular velocity, and this control signal is sent to basically to the mobile robot and its local controller, and k theta is the controller parameter selected by the user. That is, this is the proportional gain. And over here we can see the error in angle or angle error. It's simply a difference between the desired angle theta d and theta. Now again, theta c dot is the control signal, and this control signal serves as the set point for the mobile robot and its controller. However, that local controller is outside of the scope of what we will cover in this video tutorial. For us, the main thing will be to compute theta c dot. To compute that, we need to select k theta, or the proportional gain, and at every time instant we need to compute this error, and the basis of that error value k theta, we can compute theta c dot. Let's analyze this equation. First of all, if theta d, or better to say if theta is not equal to the theta d, the error will not be equal to 0, and then theta c dot will not be equal to 0, and consequently we will have to move or rotate the robot. When theta becomes theta dot, we are actually on this line BD, and consequently we are approaching this point along the straight line. And this is what we want to achieve. And here comes a very, very important point. Our controller or a feedback control system has to ensure that the difference between theta d and theta always approaches zero or achieves zero asymptotically. And this is the main purpose of the controller. The controller will always try to steer the robot toward this desired angle, that is, to steer the motion such that we move along the straight line from the point B to the point D. Of course, initially this will not be possible. However, over time you will see that the controller will do something like this, and it will actually converge to this line, which is very, very important. If you took a control engineering class, this controller for the orientation angle has to be asymptotically stable, and asymptotic stability over here means that the angle theta of time asymptotically approaches theta d. But keep in mind over here one very important thing: theta d is being changed dynamically. That is, if the robot moves somewhere over here, we will have to recompute theta d, and then we'll have to recompute errors, and we'll have to recompute everything. Next, let's focus on the linear velocity controller that will set the value of VB. Our goal is to derive the controller that will be proportional to the distance between the points B and D. By using basic trigonometry, we have that the distance between the point B and D is given by this equation. This is simply basic linear algebra or even calculus. Namely, if we know this side and if we know this side, then we can compute this side of the triangle by using the simple equations. And consequently, since this is the distance and our controller should be proportional to the distance, the linear velocity controller is simply a proportional constant, let's call it kv, multiplying the distance, and this is vc. And vc is the control signal in the form of the linear velocity, and kv is the controller parameter selected by the user. The control signal vc is sent to the local controller and serves as the set point for the velocity vb. That is, the local controller, that we will not cover in this video tutorial, will have to make sure that VB is equal to VC. Now, let's analyze this equation. When the distance is not equal to 0, then the control signal VC is not equal to 0 and the robot will move. On the other hand, when the distance is equal to 0, the control signal is 0, which means that we have arrived at this point over here. Simple as that. So let's now summarize these three equations for the controller. Here's the first equation. This will compute the desired angle on the basis of the current position of the robot. Then we are going to compute the control action in the form of the angular velocity by using equation 7. And finally, we are going to compute the linear control velocity action in the form of the equation 8. And that's it. Simple as that. And this has to be done at every time instant t. Now, let's analyze these equations. Over here, you actually see a proportional controller. However, you can easily change this controller to derive, for example, a PI or proportional integral or PID, proportional integral derivative controller. You will simply need to add additional term over here that depend on this angle error or the error angle, and that depend on this distance error. For example, you need to add an integral of the distance error in order to get an integrator over here. Simple as that. Okay, now that we understand the basics of the position controller, let's explain what we need to do in the sequel. In the sequel, we need to create a ROS2 package, ROS2 node, and to write and implement a C++ class that embeds a ROS2 subscriber object for receiving sensor information, and a ROS2 publisher object for sending the control commands to the robot. A callback function for reading sensor information. The sensor information consists of the current position, orientation, and velocity of the robot. This callback function is activated every time there is a sensor data on a ROS2 sensor topic. This callback function adds the feedback loop to the system. Number 3, a timer object for ensuring that the control function is called at fixed time steps. This function is important for enforcing the desired control frequency. And finally, we need to implement the controller function, which implements the control method. As explained previously, in this tutorial, we implement a proportional position controller. However, everything explained in this tutorial can easily be generalized to the case of implementing feedback control algorithms such as PID, LQR, and other control algorithms. Okay, let's start with implementation. First of all, make sure that the window, or better to say the terminal, running the TurtleSim node is active. Then open a new terminal, and we need to start from scratch. So here is the procedure that we need to follow. First of all, we need to source the environment and create the workspace folder. Then we need to create an empty package folder, structure and required files. Then we need to implement the source file, that is, we need to implement our C++ file. Then we need to modify cmakelist.txt and package XML files in order to add dependencies, and this will be explained in the sequel. And finally, we need to build the package and source the files by using the build command. So let's start with this first step. First of all, source the environment by executing this command. Then let's go to the home folder by typing this command. Note over here that tilde is a symbol or a shortcut for the home folder on Linux Ubuntu. Then let's create a new folder called workspace, called actually ROS2_WS, and inside of that folder, let's create another folder called SRC, where SRC is short for source. Then let's navigate to this folder, ROS2WS. We are going to refer to that folder as the workspace folder, and over here we will see the source folder. Let's explain what are these folders. The ROS2WS folder is the workspace folder that will contain everything. That is, it will contain the source code, build files, compiled files, and it will contain additional files. The next step is to create our package. That is, to create an empty package template. To do that, we first need to navigate to this folder. That is, we need to go to the source folder, and inside of this folder we need to create an empty package by using this command. So let's write this command and let's explain what this command is doing. First of all, we are calling ROS2 package create. This is a single command. Then we specify the build type. It's cmake, and then we specify the name of the node. This part is a standard part and you shouldn't change it. However, here is the name of the node. If you are completely new to ROS2, don't change this name. However, if you are more proficient, then you can select your own name. However, don't forget to adjust this name later on in the code. So let's run this command and let's see what will happen. But keep in mind, to run this command, you need to be in the source folder. After you run this command, you can see what is being created. You can see that we have created a new folder with the same name as the name of our package. Inside of this folder, we have created several files. Then we have created another subfolder inside of that folder, as well as additional folder and additional files. So if you type now this command, you'll see the folder name, and this name is the same as the name of the package, and inside you will see some files and you will see some folders, and these files and folders will be explained in the sequel. cmakelist.txt is a configuration file for the build system. This is a classical cmake file that is being adopted and changed a little bit such that it can be used for ROS2. Then over here we have this include folder, which we will not be using in this video tutorial. You can, for example, place some include files over here or some header files or something else. Then we have another package.xml. This is an additional configuration file that we will edit later, as well as CMake list. And finally, we have this source folder. This source folder will contain the source files. So let's navigate to that folder. And inside of this folder, we need to create our C++ code that implements the controller. In this video tutorial, I'm going to use Visual Studio Code as my C++ editor. However, you can use anything you like. If you don't have Visual Studio Code on your system, then I have created a separate video tutorial explaining how to install Visual Studio Code, and you have that video tutorial on my YouTube channel. So let's create a new file, click on File, New File, and let's call this file as test.cpp. Make sure that the extension is CPP and save this file inside of the source folder. And here it is. And over here I'm going to paste the file in order to save time. And I will explain this file line by line. This file actually contains around 300 lines. However, there are a lot of comments over here, and I deliberately created comments in order to explain everything. And my advice to all of you watching this video tutorial is to write as many as possible, or better to say, as much as possible comments, because someone else will read your code and you need to explain what's happening over here. And so here's the explanation how the comments should look like. First of all, you need to explain what your code is actually doing. So here's the explanation. C++ ROS2 Jazzy Jalisco code explaining how to write a disciplined C++ class and basic components for position control of mobile robots. Then you explain what the code is doing. The program reads sensor information and sends control commands through appropriate topics. The goal is to move a 2D robot to a desired location in 2D space. The user specifies the desired position of the robot in the Cartesian coordinates, and the proportional controller controls the robot position. And then you explain what the class will embed. The class will embed a ROS2 subscriber object for receiving sensor information and a ROS2 publisher object for sending the control commands to the robot. Then a callback function for reading sensor information. The sensor information consists of the current position, orientation, velocity of the robot. This callback function is activated every time there is sensor data on the ROS2 sensor topic. This callback function adds the feedback loop to the system. Then the class should embed a timer object for ensuring that a controller function is called at fixed time steps. This function is important for enforcing the desired control frequency, and the final implementation is the implementation of the controller function, which implements the control method. The controller function implements a proportional controller for controlling the position of the robot. The controller function sends velocity control commands to the robot. So this is a brief description of what your code is doing. Then you can add additional things over here. Now, in this code, I'm actually putting all the functions inside of the class definition. If you have a larger project with a number of modules or with a number of functions or with different classes, then you shouldn't follow this approach. That is, you should split the header. You should split or separate your code into header and implementation files. However, here for brevity and for clarity, I'm not doing this. Since if I start now splitting everything and the code is not too long, then it's going to be difficult to understand all the steps. Here, I placed everything inside. And over here, you specify the name of the author, and then you specify the license over here. Of course, this code is licensed, and I provided a license.txt file. So let's start. The first step is to include the necessary header files. Look what's happening over here. Our RCL-CPP is the ROS2 client library for C++ that is included with any standard installation of ROS2. RCL-CPP provides the standard application programming interface for using C++ in ROS2. That is, whenever you want to write the C++ code in ROS2, you always need to have this line. Okay, let's see what is this. Here we are including twist.hpp header file. So what is geometry message twist? It is the type of the message that this code sends. That is, the control actions will be embedded into a twist data structure. So what are the twist data structure? The twist data structure contains the components of the linear and angular velocity vectors, and this is explained previously in the tutorial. This command or this message is sent through the topic turtle1 command velocity, and we discovered this topic previously in this tutorial. Here you have to make sure that this is the correct topic and modify the code if it's not. Namely, sometimes you might have two turtles that are being created, and consequently this number might be different. You just need to go back in the tutorial and again type ROS topic info or something similar, and you will see the exact names of topics. Next, we need to include this file, post.hpp from TurtleSim message. The sensor of the TurtleSim node sends the data in the form of this data structure over here. This data structure contains the information about the position, x, y, orientation theta, linear velocity, and angular velocity of the robot. This is very important. Then we need to include chrono. We need this header file in order to work with time functions. Then over here we need to include cmath. This is the math library for C++ that actually originates from the C programming language, and we need this function in order to implement these control equations. This is very important. Then this is the placeholder for the callback function input parameter, and over here we need to type this since we plan to use time and to precisely measure the time inside of our code. So let's start with the class definition and implementation. This class implements the controller. This class inherits from the RCL-CPP node class, namely the base class for most of ROS2 C++ nodes is RCL-CPP node class. This class implements the callback function that is activated every time a sensor message is received. Then the class implements the controller function that sends control actions. Then the class implements a timer mechanism for precisely controlling the execution of the control algorithm. And over here we summarize the topics for sending control signal. This is the name of the topic, and the topic for receiving sensor information. This is the name of the topic. Then over here we call the class controller node, and over here we are saying that this class is actually inherited from RCL-CPP node. So what is the inheritance? You can think of inheritance as the process of augmenting an existing class. Namely, we have this basic node class, which is a standard ROS2 RCL-CPP class, and we want to add additional functionalities to this class, meaning that we want to add additional member variables as well as additional functions to this class. Okay, so before defining the constructor function, we need to call the constructor of this parent class, and we need to pass the name of the node. So it's done over here. Here is the constructor. This constructor accepts several things. And over here we call actually the constructor of the base class, where we specify the name of the node. So let's see what this constructor is actually accepting. This constructor is actually accepting the desired position of the controller in the Cartesian space, x and y. Here xd means x desired and u means user or user specified. So we have xdu, ydu, and then we have floats kvu and k theta u. So what is kvu? Well, kvu is nothing less than velocity parameter or the proportional parameter of our velocity, linear velocity controller, and similarly k theta u is nothing less than, let me just show you, is k theta. And these are the parameters selected by the user. So when we construct an object of the type control node, we need to specify user-defined position and control parameters, and that's it. And then we need to set the desired position and the controller parameters. Namely, this class has private member variables, and they are xd, yd, kv, and k theta. So let's see where they are. Currently we are at line 95, so let's keep this line. And if you go all the way down to the end of the class, don't worry, I'm going to explain every single line of this class, and you can simply type it. It's not a big deal. Here is the desired position, and here are the control parameters, and you can see that they are private. Okay, so let's go back to 95. Good. So what is the next step? Next, we need to instantiate a publisher that will publish geometry message twist to the TurtleSim topic. Here's the name of this topic, and it will set the buffer size to 5. So what is actually a publisher over here? Well, our controller will compute control actions according to these equations over here, and when these two control actions are computed, a data structure will be created of the type twist, and we're going to communicate this data structure by using turtle1 command velocity topic. And over here we are creating a publisher, simply like that. We are specifying the type of the message we want to send. We want to send twists. We specify the name of the topic, and we specify the buffer size. Simple as that. So this control publisher is actually, again, a private member variable. If you go, let's now first remember this line 104. So if you go to the private member variables, you'll see it over here. Here it is. Simple as that. Good. Let's continue. Now, besides the publisher, we need a subscriber. The subscriber will receive sensor information of the type TurtleSim message pose from the TurtleSim node through the topic called turtle1 pose. Here we are binding a callback function called sensor callback, and you can see it over here, that simply receives the message and stores it in the private member variable of the class called last received messages. Now, let's explain this whole syntax over here. First of all, pose subscriber is actually a private member variable, and you can see it over here in the private member variables. And over here on this line, we are actually instantiating it. That is, we are creating an object of a particular class. We call this function create subscription. The create subscription function is actually a method or a function of the base node class, that is of the parent class. Since we are inheriting everything, we are also inheriting create subscription as well as create a publisher. Then we type the data structure or the type of the message that we expect to receive, there of the type pose. And remember, the pose will carry information about position, orientation, linear and angular velocity, that is sensor information. Then we need to specify the name of the topic. Here is the name of the topic. This is the topic used to receive the message. Then over here, we are using this syntax and this function. This is a predefined quality of service profile in ROS2 designed for handling sensor data streams. It prioritizes receiving the most recent data and is configured for scenarios where losing some data is acceptable in favor of low latency and high throughput. And over here, we need to do one very important step. We need to actually bind a callback function. The name of this function is sensor callback, and this function will be defined later on. So what is a callback function? Namely, Every time there is a new message of the type TurtleSim message pose on the topic turtle1 pose, a function will be called. And this is actually a callback function. And this will be done in the background. That is, inside of our main function, we will never explicitly call a sensor callback function. The sensor callback function will be called automatically in the background. So here we are binding to this object, that is to our class, and over here we are using this placeholder, which is really not important for this particular application. Next, we need a timer object. So what is a timer object? Namely, this timer object is declared, This timer object is actually declared as a private member variable. Let me just remember 135. So the timer object is here. You can see the data type of the timer object. And the timer object ensures that the time is precisely controlled. Here the time period is 250 milliseconds. So every 250 milliseconds we want to control something. That is, we want to send control actions. And for that purpose we are creating a timer object. Then again over here, similarly to this callback function, sensor callback function, we will have another function called control function. And this function will be actually used to send control actions. And the control actions will be called with a period of 250 milliseconds, and this is actually 4 Hertz. That is, with a control frequency of 4 Hertz, we are going to control our robot. And every 250 milliseconds, we are going to call this control function. Simple as that. Note over here that we are still in the constructor function. That is, we stopped at the line 141, and if you go all the way up, you can see that we are still in the constructor. This function, that is controller node constructor, is called only once when the object is created. And we need to initialize or set to 0 certain member variables. Over here we have the control velocity private member variable, which is actually a data structure. Let me show you where it's being declared. Control velocity is actually of the type geometry message twist, since we want to send twists. Here we need to set to 0 components of the linear velocity and the angular velocity. And this is done only once the object is created. That is, we need to reset our controller. Every time step, that is every time this control function is called, that is every 250 milliseconds, we are going to change or update the control velocity. Next, we need the initial time, and we need to set the initial time as now. This initial time will be used as an absolute time with respect to which we are going to measure time. And over here, if I now go to the declaration, let me just go to the declaration. For some time it's not working anymore. Something else happened here. Let me just now do this. So I'm now at the line 158, and if I go to the declaration all the way down, you can see that this is of the type RCL-CPP time. Okay, let's continue. And this is the end of our default constructor. So let me show you the default constructor again. Here's the first part. Here's the second part. Here's the third part, and that's it. Next, we need to implement, or basically to define, 2 functions. Here's the sensor callback function. The sensor callback function is triggered actually, or better to say, it's being controlled by the subscriber object that we just created. Here it is. What do? We are receiving the messages of the type pose, and what do? We just store these messages inside of this message called last received message. And last received message, if you go all the way down, is a private member variable of our class. That is, we will always store the message we received. And what do we do over here? We record the time of the received message in order to have the time for logging and for tracking what's happening. So again, last received message time is a private member variable of our class, and you can see the declaration over here. Good. And this is the control callback function whose call frequency is specified by the timer object and its frequency. Here you should code or call your control algorithm. On the basis of desired position and orientation, the function computes the control commands and sends them as control velocity commands. So what do we do over here? Well, we are actually implementing our control algorithm given by these three equations. Let's see how this thing is being done. First of all, last received message is actually always being updated whenever there is a message on the topic. What do? We store the current position, x and y coordinates, and these are the coordinates inside of a base coordinate systems. That is, these are the coordinates of the point B. This is very important to keep in mind. Then we store the orientation angle theta, that is this angle, and now we have all we need to have in order to compute the control actions. So what do we do over here? We simply implement the equation number 6. Here it is. We call stda810 yd minus y. Oops, somehow it went all the way down. Let me go back here. Yes, yd minus y, xd minus x. We compute inverse tangent and we store in the desired orientation angle theta. Then over here we implement the velocity controller. Here we implement the orientation controller. That is, we implement this equation and this equation, nothing special. You can see how we compute powers, how we compute SQRT, etc. And then once we have x velocity, theta velocity, what do? We just form a data structure of the type twist. Keep in mind the control velocity is a private member variable, and it is of course of the type twist. Then we set the values, and then over here keep in mind that we are only setting the x component, and note over here that the twist is defined in the body coordinate system. That is, the twist is defined inside of this coordinate system and not inside of the base coordinate system. This is very important to keep in mind. So we set the x velocity and theta velocity, and all the other fields will be equal to 0. And then that's it. We simply print the message, then we publish by calling control publisher publish function, we specify control velocity, and that's it. And then finally we log. We log the information being received, that is, we log the information stored inside of the last received message. We log the time. The time is always measured with respect to the initial time, as you can see over here. Then we log x and y coordinates of the robot as well as theta. This is in the base coordinate system. Then we log the linear velocity, we log the angular velocity, and that's basically it. And here are the private member variables. Simple as that. Here they are being explained previously, and here's the second part. And this is our class. So now everything is embedded inside of the class. It's it's not simple, but it's not complex. It's actually a template that you can modify and use it in your application. Okay, and let's now look into the main function. So where is the main function? Here it is, and you can see how simple it is. So what's happening inside of the main function? First of all, before using the RCL CPP API, we must initialize it by using this function init. Then we need to pass argc, argv, which are not being used in this code, however you can use them, and this should be done once per process. This function will initialize any global resources that are necessary for the middleware and client libraries. Then over here we specify the control constants and we specify the desired position. Here I go with the kv with 0.5 and k theta of 2. Then I'm specifying the desired position 1 and 9. And over here we are creating a node for instantiating the object of controller node. You can see how we do it. We simply use auto since we want to simplify the code. We called it as test node. Then here is this pointer, make shared pointer. We specify what should be the type. And then over here we pass this to the constructor, and that's it. Simple as that. Of course, here you can use different alternatives for creating and instantiating the node. Here they are. And then once you do that, you simply need to spin the node. This will actually spin the node, set all the callback functions, set the control function, and everything will be run like a Swiss watch. And that's it. Here you need to type this. This will actually shut down the code properly. For example, if your user presses Ctrl+C, the code will not stop until everything is being destroyed. Once everything is being destroyed, then the code will be, or actually the program will be closed. And finally we return 0. Simple as that. Next, let's save this file and let's keep Visual Studio Code open. Let's go back to the terminal and let's bring our manual and let's explain the next step. Okay, now we have implemented the code. It's located inside of this folder. And next we need to modify our CMake list as well as the XML file. First of all, go one step back and over here find the CMake lists.txt file. We need to edit this file. There are several edits that need to be done, and it's very, very important that you do it properly. Okay, so let's learn how to do that. Well, let's open Visual Studio Code, click on File, click on let's open a file, here it is. Then let's go to this folder, double click on CMake lists, and let's start with modifications. So, first of all, we need to define the ROS2 dependencies. Our C++ program and ROS2 node depend on the standard ROS2 nodes and packages RCL, CPP, TurtleSim, and geometry messages. How do we know that? Well, if you go all the way up to the top of our code, the code should depend on RCL, CPP. This is actually a package. Then it depends on geometry message. Again, this is a ROS2 package. And it depends on TurtleSim, which is again a ROS2 package with all the header files. So we need to tell to our CMake that we are depending on these external header files and these external packages. So how to do that? Well, relatively simple. You just need to add these 3 lines. So let me now copy them. And so where to add these files? Well, I will add them, for example, over here after this find package. And we are here simply saying find package, RCL CPP, and this is required, find geometry message, and find TurtleSim. Let's save this file and let's continue. So what is the next modification? The next step is to define an executable for our code and node. We can name the executable simply as test program. To define this executable, we need to add this line to our CMake. So what's happening over here? We are adding executable, and the executable name will be test program, and this executable will be used to run the code with ROS2 run, then the name of the package, then the name of the executable, and we need to specify the source file. Note over here that the source file is test.cpp, and that's precisely the file we just wrote. Here you need to specify the relative path, and the relative path should be with respect to this folder in which cmakelist file is. So you can see that we are in the source, that is the code is inside of the source, so that's why you need to tell this. Okay, now we need to add this thing. We need to add the target dependencies. So we are saying mn target dependencies test program, and this test program depends on these packages and the corresponding header files. Let's save this and let's continue. Now we need to install, or better to say, we need to tell to ROS2 where to find the executables. After you build everything, the compiled files or the executables will be stored in a special folder. It will be in lib and the project name. This is not important for the time being. However, you need to say that. You need to say install targets, then the name of the executable test program and where it's being stored inside of the lib and project name. Save this and let's continue. Are these all the modifications we need to do? Yes, they are. Next, we need to add, or better to say, to modify an additional file. Go back to the terminal and type again lsla, and you will see this package.xml file. So let's modify that file. Click on File, click on Open File, and here's the file. Open it up. Here it is. And over here we need to add the dependencies. Usually I like to add the dependencies over here. So what are the dependencies we need to add? We need to add these lines. So let's do that. Here they are. Our code depends on RCL-CPP, geometry messages, and TurtleSim, which are the standard C++ ROS2 packages. Over here, if you want, you can play with the name, you can specify the version, you can give a description, you can set the maintainer email, and over here you can specify the license. In the interest of time, I will not do that. However, it's still a good practice for your code version control to fulfill or to enter all the details over here. Okay, the next step and the final step is to build a package and source file by using the callback command. Make sure that you save all the files. And let's keep this file open and let's go to the main function so we can later on change here the parameters. Okay, so let's go back to the terminal and let's see what we need to do next. We need to build this package. To build this package or to build everything, you have to go back to the base workspace folder. And the easiest way to do that is to run this command. And inside of this folder, you need to write, or actually you need to execute the callback command. However, before we build the project, we need to make sure that all the dependencies are installed on the system. The dependencies are RCL-CPP, TurtleSim, and geometry messages. To check all the dependencies, we need to use ROS2. To install ROS2, we need to type this and enter your password. Then you need to initialize and update. If you see some errors during these steps, simply ignore them. And over here, let's update. Okay, and let's wait. Now, let's verify that all ROS2 dependencies are installed by running this command. And all required ROS2 dependencies are installed successfully, which means that we can continue. Then, make again sure that you're in the base folder, and then you simply need to type this command. So this command will build everything, and over here we are actually selecting only a single package since we have only one package and it's called test node. Let's press enter and let's hope that there will be no errors. So let's see what happens. Bang, bang, bang. So far so good. No errors. Starting, finish, summary, one package finish. No errors. There might be some warnings, maybe in the code, for example, over here, instead of, for example, double, instead of float, I need to use double or something like that. However, these are the minor warnings, and probably you can look into the log, and it might be a good idea to look into the log, and this will be explained in the future video tutorials. Good, let's continue further. So what's the next step we need to do? Well, the next step is actually to run everything. So how to run the created node? So let me show you how to do that from scratch. Open a new terminal. And over here you need to create an overlay. That is, you don't need to source the underlay, you can just source this file setup.bash and know that this setup.bash is actually a setup file or a configuration file inside of the newly created package. So let's run this, and this is the only necessary step, and then after that we can run the code. We run the code like this, ROS2 run, then we specify the name of the package and the name of the executable. Now go back here to CMake and find the name of the executable. Where it is? Here it is. It's test program. Simple as that. Here, and let's now open up the TurtleSim and let's see what will happen. The turtle should go from this position to somewhere over here, since if you look into the code, the desired position is 1, 9, and 1, 9 is in x1 and 9 in y, that is, it's somewhere over here. Okay, so let's run and let's see what will happen. Let me put it here and then bang. Boom! Awesome! You can see over here and you can see the x position, how we are approaching, y position, we are almost there. Of course, here there is no friction, so you don't need to use integral action, and you can see that we have arrived at our destination. And you can see linear velocity, you can see angular velocity, which is good for logging. And that's it. Now let's change some code parameters. So for example, let's go with position 9, 9. Okay, let's save this. Now since we modified the code, we need to go back inside of this folder. Then what we need to do, we need to build everything again since we modified the source file. Then let's go back to this folder. Let's do Ctrl+C to close. Then we need to source again setup.bash file. Then what we need to do here, we need to close the current TurtleSim. Let's create a new TurtleSim. Let's put it here. And over here, if I now press, or actually if I execute this, new code will be executed. Okay, so let's run this, bang, and we go to 9, 9, beautiful. Here we are. This is really, really nice. Okay, now let's investigate several things about this code. Let's open a new terminal, and inside of this terminal, let's do several things. First of all, let's see what's happening behind the scenes. Let's source again the global environment, that is, let's create an underlay, and let's see our topics. And let's make sure that the topics are as they should be. We can see they are. Then let's now see the nodes by running this command. And we can see not only TurtleSim, we can also see controller node, which is our node. Let's see what type of messages are being sent through the topic turtle1 command velocity. This is actually the command velocity topic, and you can see what's being sent, very small angular velocity. And now since the system is in steady state, you can see it's not moving anymore, nothing is actually being sent, we are in steady state. Okay, let's now do several additional things. Press Ctrl+C to stop this. Let's now install RQT graph by typing this, and let's call RQT graph to see the structure of our system. If you see here, you now can see how our node look like. You can see all the topics. This is really beautiful. And that's it. Now we have investigated everything and we are 100% sure that everything works as it should. Okay, that's all for today and thanks for watching.